Are you tired? Are you afraid? The solution begins here. This adaptive logic is the engine of autonomy, navigating chaotic streets and mastering complex physical tasks. But the potential goes far beyond robotics. It's about optimizing the foundational layers of technology and unlocking the energy solutions of the future. Universal logic, infinite high-value markets, smart moves, real impact. Kassler, the future is your next move.
Okay. We started with the AI chess, but the real value lies beyond the chessboard. The underlying AI energy can safely and optimize decision making and can be directly applied to industries such as pricing, supply chain, energy, and finance. Today we are using AI to win chess games. Tomorrow we will use it to help a business win profits. Um, this graph shows the global AI market size from the 2024 to 2035, 34 years. 34, and we can see that the AI market is growing very fast every year. This means AI technology is becoming more important in many industries, and the market size market will continue to expand in the next 10 years. And this chart shows AI growth value added in 2035 across the different industries. It compares two things. The light blue section is baseline value without AI, and the dark blue section is additional value created by AI. We can see that AI brings a lot of economic impact in many sectors. For example, manufacturing, AI adds most value here, almost $12 trillion, and wholesale and retail also get a very big boost from the AI. And these are two real-world examples. We can see that DeepMind uses AI to optimize the coding in Google data centers by learning from the thousands of sensor ratings and choosing the best control action in real time. And the system cut cooling energy used by up to 40%, and this means saving millions or even trillions dollar, tens of millions dollar. And we can see that in right side, the blue section representing the market share of autonomous driving technology, and it's gradually increasing. As the autonomous vehicle market has proven to be more than just a niche market, potentially generating $400 billion in revenue by 2035.
Typically training against random opponents, which limited the quality of self-play. Our system dramatically selects and adjusts opponent styles, making the entire training process more effective. Our opponent selection mechanism is highly generalizable. It is not limited to chess. It can be applied to robotics, simulation, automatic driving, and multi-agent games. And you can find this is our model architecture. After the players make a move on the front end, the board state is sent to the RL agent. Our RL agent uses three modules, DQN, OJEC, and DDC, to understand the opponent's style and adjust the different way to play. The OJEC is the Opponent Guide Exploration Controller. We change how much the agent explores depending on the opponent explorer, because when our opponent is aggressive, we can try to choose the explore less ways. But when the opponent is defensive, we can try to find the many choice and explore many ways. The DDC is a dynamic difficulty curriculum. We can choose the next opponent based on how much we've been win right now. When our opponent is so difficult and our win rate is so low, we can choose opponent easy. It become easy. But when our win are many times and our opponent is so easy, we can choose the more difficulty ones. During the training, the model plays many games against difficult and easy, and there's different types of AI opponent. All game experience are stored in a player buffer, and the GPU training the model in benches. And the win rate and the reward data are saved in the database to evaluate how well the model is learning. And you can find this is our win rate and the average reward. The basic DQN is the blue lens, and our OJEC and the DDC new model is the yellow lens. You can find the average reward. At the beginning we are less than the blue lens, but after 1,000 episodes, we can find our yellow line is become higher and higher. And it also can be find in the win rate comparison. We can find that our new model's win rate is bigger than the basic model.
Hello, Professor and Grader. In this part, I will present the second strategic root of our system, the planning engine of Kastler. Well, this stage is where Kastler becomes more than a typical reinforcement learning agent. Well, this is second stage. It learns strategy through self-play, and it trains a policy and value neural network, and then it performs a Monte Carlo tree search to simulate the futures before selecting each move. Our architecture is dual root. The first stage learns to react. The second stage learns to plan. And these two forms of intelligence complement each other and form a more flexible and more general decision engine. Okay, so here's the training scale. And as you can see, here's the cumulative stages page. And during the training, the engine generated for approximately 130,000 full chess games, and it evaluated 9.8 million unique board states. So it explored tens of millions Monte Carlo tree search nodes, and it was all done on a single GPU in about 3 hours. So these three numbers represent 3 levels of capability, which is game count, that this engine can generate its own experience. The second part is the state count. It can learn from millions of examples. And third is search nodes, that this engine can perform long horizon planning. So importantly, this entire dataset is self-generated. There's no human supervision, no heuristics, and no opening books involved. And here's the loss convergence. And this learning curves helps us understanding with this model internalized. On the left is the value loss. It converges to around 0.001, indicating that this engine develops a stable sense of long-term positional value, what we can think of as a strategic intuition. On the right, this policy loss steadily decreases, showing that Kessler is refining its action preferences. On the right, the policy loss steadily decreases, showing that our engine is refining its action preferences and shifting from the random exploration to a consistent strategic behavior. So in short, our engine is not memorizing moves. It is a learning strategy through millions of self-play interaction. Okay, so here's the original screenshot that has the results for the total 16 rounds of training. And as you can see, here's the total states evaluated, which is 9.8 million. Well, before moving to evaluation, I want to briefly highlight a few parts of the implementation to show that our engine is a fully engineered system built from scratch. Well, first, this is the parallel self-play module, and we batched hundreds of ball states into a single GPU tensor, and we run one forward pass of the policy and value network. It will mask illegal moves and sample using the temperature, and this pipeline enables our engine to produce over 9 million training states. Secondly, this is the part of our Monte Carlo tree search implementation. We compute a PUCT scores of the tree selection. It will expand the leaf nodes in batches and evaluate them together on the GPU for the efficiency. Lastly, at the root, we use a numerically stable log softmax to prevent the overflow and ensure the robust move selection. So all of this is wrapped in a clean engine API that any UI or application can call to request a move. We also evaluated the engine against a random agent over 20 games. At this training scale, our engine achieves 0 wins and 8 draws. Although this model is far from competitive strength, it shows a basic stability. It often avoids the immediate blunders in steering many games into a draw endgames. This result also highlights a key insight that a full chess has enormous complexity, and meaningful win rates require training scales that go far beyond what we can achieve in a classroom setting. So our focus here was building a complete learning engine, and that engine is fully functional. Finally, I will demonstrate how our engine connects to our UI. The UI serves as the front-end interface, while the actual move decision comes from the Kessler engine in the terminal, and I will input a human move in the UI. For example, here's the original chessboard, and here's the human move. Okay, as you can see, this is the human move. And then we will take the AI suggested move from the terminal, and I will apply it back into the interface. H7, H5. That's it. So it shows that our engine supports an end-to-end workflow from neural inference and MCTS all the way to user interaction. So to summarize, our engine combines two complementary intelligence routes, a reactive reinforcement learning route based on DQN, and then a strategic planning route based on self-play and Monte Carlo tree search. The result is a modular, self-evolving decision engine which is capable of generating its own data, learning from it, and playing a full chess games end-to-end. And chess is only our first domain. Thank you very much.